Welcome back to McMaster University course Computer Science and Software Engineering 2FA3, Discrete Mathematics and Applications 2. We're going to start today on the last part of the sixth topic, Turing machines and computability. This part is entitled Undecidable Decision Problems. Before we start with this topic, we need to do a little bit of a review. So I want to talk a bit about cardinality. So every set has a size or cardinality. So for instance, if I had the set of 1, 2, 3, 4, 5, we would say the size of that is 5, the cardinality is 5. And I could have another set, let's say A, B, C, D, and E. This set is a different set. Its size is also 5. Its cardinality is also 5. And we can say that these two sets have the same cardinality because there is a bijection which maps every element in the first set to an element in the second set in such a way that the mapping is total, it's surjective, and it is injective. In other words, it establishes a one-to-one correspondence between this set and this set. So we say these two sets have the same cardinality and their cardinality is 5. Now, this idea works for infinite sets as well. So let's say I had the infinite set, which I'll write like this. I have an infinite set of the even natural numbers, which of course I can't write all of them, but you know what I mean. And now let's say I have a set of all the natural numbers. And so forth. Now, these two sets are infinite, and they're not the same set, but they have the same cardinality, because I can have 0 be mapped to 0, 2 mapped to 1, 4 mapped to 2, and so forth. Basically, every number here is mapped to 1/2. We divide this number by 2 to get to what the number it gets mapped to. So we say that these two sets have the same size, the same cardinality. The cardinality is called omega, or sometimes it's called aleph 0, the first character of the Hebrew alphabet. So it's called either one. So this set, these two sets, even though they're both infinite, they're not the same. They have the same cardinality. Okay, so what I want to do now is take a look at all possible sets. Let's say these are all possible sets. Better yet, let me draw it as a box. So we have all possible sets here. And some of these sets are finite. And then there's some sets that are countable. Countable means there's a bijection. I'll say B from the natural numbers to that set. And then we have sets that we call countably infinite. Those are sets here. So countable sets include finite sets. So this was a set like I showed you before, where you had 1, 2, 3, 4, 5, and the natural numbers would be an example of a set that's countably infinite. So here's the important question: is there some set out here which is not countable, which we call uncountable? And what that means is if it's a set uncountable, and I start off with the natural numbers like this, and I have this set that's not countable, if I do this mapping, if I do a one-to-one mapping like this, no matter how I do it, if this is uncountable, there's going to be parts that never get mapped to, no matter how I do it. Because this set, if it's uncountable, is fundamentally bigger in size than the set of natural numbers. So that's the problem we're interested in looking at. It's the problem of, are there uncountable sets? Now, this is relevant to our course for two reasons. If we know there are uncountable sets, then we're going to be able to say things about undecidable problems. And the proof that there are uncountable sets is using a method called diagonalization, which is a very important method of proof that's used in computing all the time. And in particular, we're going to use it to show the existence of an undecidable decision problem. Okay, so what does Theorem 3 say? This is a theorem that was proved by Georg Cantor, 1891. It says there does not exist a bijection from the natural numbers to the power set of the natural numbers. So that's the set of all subsets of the natural numbers. Since there's no possible bijection, and we know that the power set is it's of size at least the same as the natural numbers, this says that this set must be uncountable because there's no bijection. So we want to prove that there is no bijection. And as I said, this proof is by diagonalization. And the proof is pretty simple. We assume that there is a bijection. We assume there is some bijection F. And then that bijection can be displayed as this infinite two-dimensional matrix. And so on the top here, we have the natural numbers, 0, 1, 2, 3, 4, and 5. And on the side, we have a listing of the subsets of n. So the first natural number gets mapped to the first subset, the second gets mapped to the third subset. And because f exists, if we go down this way on the left, we will see every possible subset of n. And if we take a particular subset, let's say the subset that 2 is mapped to, and we look at this infinite sequence here, this infinite sequence tells us what the set is. Because there's a 0 here, it says 0 is not in the set. There's a 0 here, 1's not in the set. There's a 0 here, 2's not in the set. There is a 1, so 3 is in the set, 4 is in the set, 5 is in the set, and so forth. So each line describes what these sets are. Okay, so we're assuming we have this bijection F, and every possible subset is listed in this big matrix. Okay, so what I'm going to do now is I'm going to define a set. It's called D. And D is going to be a sequence of zeros and ones. And so it's going to define a set just like each of these lines. It's going to be a sequence of zeros and ones. And it's going to be defined as follows. The mth member of this sequence will be 0 if if m is a member of f of m. So I go down and find f of m. I go over to m, and I see what's there. If there's a 1 there, I'll make beta m 0. If m is not there, which means there's a 0 there, I'll make beta m 1. Okay, so if you look at what beta m will be, let me use a different color here. Beta m will have a 0 here, because we had a 1 here. Instead of let me write it up here. You'll have a 0 here. And because there's a 1 here, you'll have a 0 here. And because there's a 0 here, I'll have a 1 here. So I can write what it is. Now the interesting thing is that BDM differs from f of 0 right here. It differs from f of 1 right here because I've always changed whatever f of 1's point there to the opposite. It differs f2 here, it differs f3 here, it differs f4 here, and so forth. It differs with all of these. But how is this possible? Because f is a bijection. Every possible subset of n is listed here. But this is a subset of n, and it can't possibly be here. Our conclusion is that there is no such f. There can be no such f, because if there is such an f, we can construct a set, which we'll call the diagonal set, and this set cannot possibly be in our matrix. So this is a contradiction, therefore there is no possible bijection, therefore P of n, the power set of n, the set of subsets of n, is uncountable. Okay, so this is a really important result. This result really shook up a lot of mathematicians in the 1800s. And this is the beginning, this is one of the results which is the beginning of modern day set theory. Okay, so what does this have to do with undecidable problems? Well, we can now prove that there exists an undecidable problem. How do we do that? Well, if we consider, I should say, undecidable decision problem. How do we do that? So we can think of a decision problem as, we can get a bunch of decision problems by thinking of the problem of determining the membership in a set A, which is going to be, I wrote it as a subset of the power set of n, but what I should have really said, it should have this, should be subset. It's a member of the power set of n. Let me just, if you say that A is a member of the power set of n, that's equivalent to saying that A is a subset of n. Okay, so if we take a member of the power set of n, that gives us a decision problem. The problem of whether a natural number is a member of A or not. Now we know by the theorem we just proved that this power set of n is uncountable. So there's an uncountable number of decision problems. However, there's only a countable number of Turing machines. This is because, well, you can think about with Turing machines, we always have a finite input alphabet, we always have a finite tape alphabet, we always have a finite number of transitions in a transition function. So there's only a countable number. Another way of seeing that is that we can encode every Turing machine by a string of zeros and ones. We will see that in just a moment. And we know that the numbers of strings of zeros and ones is countable. I can count them. Let me give you a quick example how I can count them. Let me get different color. If I have all the natural numbers, and let's just say we have a string of zeros and ones, we can start with the empty string, and then we have the string of 0, then the string of 1, Then we have the string of 0, 0, 0, 1, 1, 0, 1, 1. Then we have strings of length 3 and so forth. And obviously, I can set up a bijection. So if we jump back to here, we know that we'll see in a moment, we can encode any Turing machine by a string of zeros and ones. And this means that there's only a countable number of such strings, but there are an uncountable number of these decision problems because there's an uncountable number of subsets of the natural numbers. So, therefore, if we are going to be able to come up with a way of deciding membership in these sets, there's only going to be a countable number of Turing machines we can use by the Church-Turing thesis, which says basically every algorithm that we have can be implemented as a Turing machine. So we have only a countable number of algorithms, but we have an uncountable number of decision problems of this form. Therefore, there must be some undecidable decision problems. So this theorem shows that there are undecidable decision problems, but it's non-constructive. We didn't construct a decision problem that's undecidable. We just showed there must be. And so the big question is, what is an example of an undecidable decision problem? And this is what we will be talking about next time. Okay, so this is Bill Farmer stopping here, and we will begin looking at a specific undecidable decision problem next time. Goodbye.